All right, I will begin. Once I begin. Dear Father, we again thank you. We thank you for the rain and for the rain which refreshes the earth, and we thank you for all your many blessings to us this day. I pray that you be with the students, help them to ask good questions today as they think of them, and just help us to all understand a little bit more about your creation today, Lord. In your name I pray, Lord Jesus. Amen. So, uh-oh. Huh. It's not a good feeling. Where are my keys? Huh. Well, that's not cool. Last time this happened, I ended up spending a half hour at the end of the day only to find out they were back on this lecture where I left them in the morning. So that's already been ruled out. Odds are they're in my office door upstairs. It's not optimal, but all right. Oh, hey, before I forget, Riley Ham. Riley, here is yours back. You did get a couple of points back there. Yep. So yeah, if I think I've regraded most of your tests, but on the trig substitution problem, midway through the grading, I got confused. I thought it was worth 15 points instead of 10, and so I took points off as if it was a 15-point problem rather than a 10-point problem. So most of you have already corrected it. If you haven't, and it matters to you, you can still bring it to me. Just saying. All right, so let me get into the math here. So applications of differential equations are many. The one I'd like to talk about today a little bit is physics. In particular, one-dimensional physics, right? So let's talk about that. So what do I mean one dimension? So basically the idea is we're focusing on, just one-dimensional motion. This is, of course, an approximation. As you know, the world is not one-dimensional, but so like generically speaking, of course, the truth of the matter is that the net force is a vector, right? And that net force is equal to the mass times the acceleration, right? And these are vector statements which must be treated as such, as you have seen if you're in my physics course, right? But as you've not seen in my physics course, you can also introduce momentum, which is the mass times the velocity. Then your net force is equal to what? So m dv dt, right? And the way vectors work is if the mass is constant, you can bring the constant inside the differentiation, and what you have then is d dt of mv, all right? Which is, in fact, dp dt. And so the proper understanding of these things is as vectors, right? But in one dimension, we don't need vectors, right? We can just write simply what? We have f equals ma, right? Where a is equal to dv dt, and v, let's say for the sake of discussion here today, is dx dt, right? So in one dimension, we just use x for the position. We don't need the vector concept, right? Plus goes in the positive direction, negative goes in the other direction, right? That's our directionality, is the sign plus or minus of the variables. We can still talk about momentum, right? Likewise, the momentum is mv, right? And you can still say that, that the Newton's law, actually, the net force is equal to dp dt. This is still actually Newton's second law. All right, and as you discuss physics more fully, you learn that that's actually the real Newton's second law, in the sense of that Newton's second law covers the case that the mass is variable. See, if the mass is variable, we haven't even dealt with that. If you're in my physics class right now, we have never talked about a variable mass, have we? No. And Professor Dromby hasn't either, because she also has not introduced momentum yet. That's about 2 weeks from now. Or about a week from now for us, I think. Anyway, so there you go. These are the equations of physics. Now, furthermore, well, I guess I should just give a laundry list here. What are some important net forces? So generically speaking, the net force, generally the net force is a function of what? It's a function of position, velocity, and time, generically speaking. But here's some common examples, all right? So let's just list them here. You have a spring force. Minus kx is the spring force, right? You have the force of gravity near the surface of the Earth. This would be, F equals to plus or minus mg. The plus or the minus depends on what? Depends on whether you're pointing up as positive or down as positive, right? If up is positive, F is equal to minus mg, right? Because gravity does what? Goes this way, right? So you can also talk about the thrust force on a rocket, right? Rocket thrust, you can talk about, which I don't really have a formula for. Usually I just give that as a constant. Another example would be, of course, friction force, right? And so friction force, velocity dependent. Now the kind of friction force we talk about in physics, it's not usually velocity dependent. Usually we talk about the friction force, which is just, constant and related to the normal force, right? Mu mg, or mu Fn to be more accurate. So this is the velocity dependent friction force. This is the friction force that's associated with like motion. For example, for most cars at low velocities, the friction force is proportional to like the square of the velocity. But if you go to higher velocity, the friction force is more like proportional to the cube of the velocity. That's why aerodynamics become more and more important for very, very fast cars. Because as you cube the speed, it gets bigger and bigger, right? So that's why the spoiler on your Civic doesn't matter. But if you happen to have a Lamborghini Huracan, maybe it does. I don't know. Let's see here. Anybody driving a Lamborghini in here?
Yeah, anyone driving a Civic?
Civic? A car? A Civic. Let's see here. How about, what would be appropriate? What are you guys driving?
Saturn.
A Saturn? A Saturn? How sad. Prius? Oh, okay. Okay, that's good. No. You don't have you have a Tesla Plaid? Or is it? No. Okay. Well, anyway, you guys get the idea. This would be an external sinusoidal force. So something like this would be an external sinusoidal force, like something like. Now I got to be careful here. I got into trouble with this the other day. Oh man, this one's no fun at all. They put booties on it. It's kind of. If you've been in my physics class, it's much more fun. But it's fun. So sinusoidal force is something like that. Oh man, come on. This, right? Sinusoidal. Back and forth, like that. A cosine omega t. Anyway, these are all examples of forces. And you can then, what do you have to do to find the equation of motions? You have to do what? You have to solve. You put these formulas and you set them equal to the mass times acceleration and you try to solve the differential equation. That's physics, right? Or you could set them equal to the time rate change of the momentum and try to find the momentum as a function of time. You could take that approach, right? But at the base of it all, physics is a differential equation. So let me do a short derivation for you. If we have m dv dt, which is acceleration, right, is equal to the force as a function of x, right, then we can do a trick here, which is we can change that to, this is only good for one-dimensional motion, right? Because otherwise it wouldn't make sense. I mean, even one-dimensional motion, this is a little bit sketchy. Is it clear that you can write the velocity as a function of x? See, because that's what's needed for this step I just made. I'm saying, you got to understand, this is a sneaky step. I'm saying take the velocity, which is a function of time, and rewrite it as a function of position. If you do that, You're all good. If you do that, then what you're looking at, well, you're looking at the chain rule, right? Yes, sir.
Okay, can you explain this that when you went from dvdt to dx dt over dvdx, because you did that on one of the
Yeah. So what I'm doing is, I mean, if you want to be more pedantic, I should put a tilde on here and say that's really a new function. I'm rewriting velocity as a function of position. So that assumes, of course, that you can write time as a function of position and then plug it into the velocity, which is a function of time. Anyway, long story short, it's the chain rule. That's what it is. So this is the chain rule. You can think of the dx's as canceling as a sort of mnemonic here if you want. But what we have then is m dv dx, right? Excuse me, my bad. We have m v dv dx equals to f of x, right? Now, hey, this is a differential equation that we can solve, right? How do we solve this? Dx to the other side, right? So you got your m v dv is equal to f of x dx. Then we do what? Integrate, separate, integrate, right? Separate, integrate. And we'll integrate over matching bounds. So on the left-hand side, I will integrate from, say, v0 to vf. On the right-hand side, I will integrate from x0 to xf. All right, and what's that give me? So this integrates to 1/2 mv squared, yeah? Evaluated from v0 to vf. The other side is what it is. I mean, I could go further if I gave you a formula for the force, but otherwise we're just going to have to leave it like that. All right? What are we looking at? This is 1/2 mvf squared minus 1/2 mv0 squared. On the other side, we have the integral from x0 to xf. Can you guys tell me what this is? It is the timeless equation, is one good way to look at it. That's not wrong. That is what the timeless equation is. In fact, the timeless equation is, well, it is conservation of energy. That's the truth. That is what that is. But what this is the work energy theorem for one dimension. See, because what it says, what this says, this is the change in kinetic energy. Right? Kinetic energy is 1/2 mv squared, yeah? We all agree with that. On the other side, you're doing the integral of the force over the distance. That's the work. That's the work being done by the force. This is work done by F. And what can you say about F? What kind of force are we talking about? If we've set ma equals to F, that means we're talking about the net force, right? So the net force is the one which is equal to the mass times the acceleration. Now, of course, we're not going to get into like net versus constituent forces in here because this is not physics. I'm just saying it for the sake of the broader conversation that you're having this semester with physics, right? If you're not having physics this semester, you will at some point, right? If you're taking this course, you're taking physics. Pretty sure. Am I wrong? Anybody in here taking this course not taking physics? How dare you? No, you already took physics?
I'm not an engineer.
You're not engineering. Wait a minute, what's your major? Biochem. Biochem doesn't care about physics? How dare they? Oh, you take it later. But you will take it, right?
Yeah.
Okay. Phew. Phew. I mean, it also horrifies me that there are physicists, excuse me, words, engineers who are not taking chemistry. Like, to me, not taking chemistry as an engineer, that's nuts. Like, you need to know about the world, right? Does chemistry matter to industry and like manufacture of goods and design of goods? Yeah, chemistry matters a lot. I can't imagine not having chemistry in my university degree. If I didn't have it there, I would put it there as a student. Anyway, I digress. Okay, yeah, go for it. Do you need to know physics? Well, yes and no. The homework answers your question, I think. So, the calculus side of it you need to know, right? So, Am I going to like ask you to draw a free body diagram in here and start doing stuff with vectors? No, certainly not. If you can do the homework in here, you should be good for the test as a general rule. So, okay, so moving on. So that's the work energy theorem. Now there's a special kind of force, right? There are so-called conservative forces, right? What's a conservative force?
Trump.
Trump? So you're redefining conservatism. Very good. All right, so, sorry. Paleo-conservative, neo-conservative, like what kind of conservative? Liberal conservative. Do you, okay, well, I'm getting in trouble. Let's see here, F. So, in terms of a vector formalism, you do this. This is the gradient. What is the gradient? Well, the gradient in 3 dimensions is this. Partial u, partial x, partial u, partial y, partial u, partial z. Welcome to the future. This is calculus 3. Partial differentiation. It's actually not a big deal. It's actually so low tech I cover it in my physics course.
What's that first? Is it like an O or is it a?
Oh, what's this? Or what's that?
What's that?
This guy is nabla. This guy is red partial. It's not a D, it's a kind of funny looking symbol. What that means is that you're differentiating with respect to variables which are held independent. I don't want to get into it here because that's calculus 3, okay? But we need it in physics, we don't need it here. My point is, for the larger context, this is what a conservative force is, all right? In 1 dimension, this specializes. In 1 dimension, what does this look like in 1 dimension? In 1 dimension, you just have F is equal to minus du dx. So a conservative force is simply one which is the derivative of another function. That other function we call the potential energy function. So here this is U equals the potential energy. So what happens if you integrate from x naught to x f of, f which is conservative? What's that look like? This is easier, right? So you got minus du dx, dx integrate from xf, x0 to xf. What's that give you? We're integrating a rate of change, right? That's an easy integral. What's the antiderivative? Well, it's minus u, right? So we've got minus u of the final position plus u of the initial position. In other words, minus the change in potential energy. So you put these two things together, put the work energy theorem together for a force which is conservative, what's true for such a system? If the net force is conservative, then we get the change in kinetic energy is equal to minus the change in potential energy, which you can rewrite as being, if we define energy to be the kinetic energy plus the potential energy, right? Which in this case would be 1/2 mv squared plus u, which is a function of x, right? That's the total energy, total mechanical energy here. Well, that quantity is conserved for the motion. We could also prove this directly from the differential equation. That might be a useful exercise. So if you've got ma is equal to minus du dx, right? We could take that, we can rewrite that as m dv dt plus du dx equals to 0. And then there's a beautiful trick which works in many contexts, which is to take the equation of motion and then multiply by the velocity. if you multiply this by dx dt, what happens? You get m dx dt, dv dt, which I really should have just left as v dv dt, my bad, plus dx dt du dx. It's better for us to write it out for that one. So I'm just multiplying by v. And that I am the worst cameraman. Who's missing today? Austin, that guy. Let's see. All right, so then here's the trick: is this you can rewrite as the derivative with respect to time of 1/2 mv squared. Search your heart; it's true. So if you do the chain rule on this, you differentiate the velocity squared, it gives you twice the velocity times dv dt. That 2 cancels with the half to give us back what we had to start with, which was mv dv dt. So that's just a chain rule. And the other term is, again, the chain rule. But here we're thinking of, writing the potential energy as a function of time. So anyway, long story short, here we go. This is the total mechanical energy. Here it is, energy. And if the net force is conservative, the energy is conserved, meaning that it's held constant through the motion, right? You can either derive this with an integral argument like we did, or you can derive it directly from the differential equation if you have a little bit of sneakiness, like I do here. All right. So anyway, I wanted to show you these things because I think it's important to see them in one dimension. And it should help you make more sense of physics. Now, what happens if the, I don't want to go through all the calculations here, but if you read page 17, I then show that if you have a friction force added to a potential, like if you have a friction force, let me just write down the result, not do the derivation. But, question? No? If you have a friction force, if your net force is like, a conservative force, so minus du dx, so that conservative piece, but then minus or plus b times v to the n, so this would be the friction force, all right? Then by a similar calculation to the one I just did here, you can show that the energy is not conserved, but in fact the time rate change of the energy is equal to, it's proportional to the friction force, and you do v times the absolute value of v to the n, as it turns out. So for example, if n equals to 1, you get dE dt equals to minus bv squared. So the change of energy with respect to time drops off as the velocity squared if your friction force is in fact just linearly depending on the velocity. Yeah?
Is there a reason why you did minus or plus instead of plus or minus on it?
It's just to address the possibility that, like, we want the friction force to be slowing it down, so I need the plus or the minus depending on the direction of the motion. I think you could just write it in terms of like absolute value of the velocity if you wanted. But so anyway, there's that. That's just a comment. An interesting thing, of course, is what if you're dropping something, right? And you reach that, what we call it, terminal velocity. What does that mean? It's not accelerating, right? It's not speeding up further. So if you set, basically, if this is equal to mass times acceleration, right? So if your acceleration is equal to 0, then you can solve this equation. So this would typically be like mg or whatever, if the conservative piece, right? And then you can solve that equation to find the terminal velocity. But all right, anyway, enough about all this. I have more specific examples I could show you, and I'll do that, but I want to stop this for now and leave you guys time for homework questions, because that's the other thing I wanted to make sure I had time for today is if there's a homework question, you can throw it out there now. So, yes, sir.
On
Is it okay if I erase everything? Okay. On the what?
the orthogonal trajectories question on the homework.
Mm-hmm.
So I did implicit differentiation, and then I took the reciprocal and everything and found the integral.
Yeah.
And then I didn't know what to do after that to like solve. Like what are you supposed to what are you looking for to solve for the trajectory?
Well, it's a family of curves. So I think if you implicit differentiated, you found the differential equation for the given curve, right?
Yes, sir.
You flipped it over and put the minus on it to find the differential equation for the orthogonal trajectory, correct? And you integrated that, separated, integrated. You're done. That is the answer.
I thought you had found like a point or something like that.
I don't think so.
Yes, sir.
The answer is an equation that has a constant in it.
And what's the specific answer?
I don't know. Let me double check. Which problem are we talking about?
54.
Oh, by the way, were you able to get the that D-field software to work or whatever? I posted the, no?
I could not. I couldn't open like the jar file.
Ah, curses.
But what I did was, I went to the online one you said was like garbage.
Mhm.
Use that.
Oh, okay.
So,
The GeoGebra is hard to break. Like, it works, and so that one is not problematic. For the one I gave you guys in the homework, it works okay.
yeah.
But of course, then you have to like fiddle with it to actually get the points that you want. I mean, I don't forget. Did I ask you guys to find? So you were able to adjust the thing to put the 2, -2, 1 in to see it or whatever.
I think so. Yeah. I mean, I can
Because-
click on it and show the curve.
Okay. But I guess the question is, did I ask you guys to find a solution curve through a particular point? Because if I remember right, the GeoGebra one has the points kind of like built into the.
I don't think you asked for a particular.
Oh, okay. Then it probably is fine. Yeah. That's fine with me. But yeah, this is the continual annoyance I have with the other thing is that ever since there was something that happened with Java about like 5 years ago, it's been very like unreliable depending on which platform you're on and things. And I don't know. It's to me, this is why I get disinterested in computer stuff. It's like, you know, well, we looked at a solution I wrote to a differential equations problem in 2006. It's just as correct now, you know? If we tried to use the computer programs I was using to look at math in 2006, they're all gone. It's very frustrating. 54. Yeah, so I just say find the orthogonal trajectories to the curve. And so that's going to be a family of functions. And so I would expect some kind of like level curve. What's a level curve? Level curve is just essentially something of the form f of x comma y equal to a constant. This is a level curve.
So you want the constant on the right side?
It doesn't have to be. Doesn't have to be. But it should be an equation that involves a constant, and you know, theoretically, what's going on is that for different values of the constant, you get different curves, right?
Yes, sir.
I mean, that's how this works. You know, easiest example of this, something like x squared plus y squared equals to, you know, r squared. So for different r, you get circles, right? This is as r is indexed, you get not one curve, but a family of curves, right? Or if you have y equals mx plus b for a fixed b, let's say 3, right? What's that? Well, that's the family of curves that goes through, all have y-intercepts of 3, you know? So it gives you a family of curves, something like that. That's what I'm saying. It doesn't have to be on the other side. There has to be a constant somewhere if you're going to have a family of curves, right? Because that constant, as it varies, gives you different curves. It's indexing through some family of curves. Yep.
I'm kind of confused on how to set up 47 with the non-tangents and circle. That's not really how to start.
Oh, well, I think there what you want to do is to read the notes and understand what I did in the notes and then go off that. So that would be my advice there. So study like pages let's see here, study pages 6 and 7, basically pages 6 and 7 in the notes, because essentially I do something very similar in how I build example 9. If you understand how I built example 2.9, you should be able to answer that question, I think.
Which notes are those?
The first order, the article, these ones. Other questions? Yeah.
On number 58, you say y prime is y.
One second. 58, I say what?
Y prime is the y dt, and we're not given y as a function of t. Should we leave our answer if there's something y?
Oh, I solved this in class. We solved this one Wednesday. I might have used X. No, I used Y. So this is the one that worked out to sign. What was your question again, though? I want to understand your question.
We weren't given y in terms of t.
Y in terms of T. Well, yeah, that's the thing is we change variables. We changed variables to V, and then we did the trick that we did today. I just erased it, where we changed the dependent variable from T over to Y, I think. Or did I use X? I'm sorry, I can't remember.
You use X.
I used X, but sorry, I can't remember. I didn't. Just a second here. Like, I didn't mix X and Y in that example, did I? I sure hope not. No, so this would, like example 5.9 is essentially the solution to this homework problem. That's what I'm getting at, and that's what I worked out. I want to say Wednesday. But to answer your question directly, right? So here's the thing. So you got y prime prime plus y equals to 0, right? Which is dv dt plus y equals to 0, where v is dy dt, right? And you're right. That's an impossible ask to solve this, right? This is not a reasonable thing to try to solve. Why? The question you're asking is good, and it deserves a response. Why didn't I try to solve this in class? Because I didn't, right? We skipped right past this. We just went past this because we knew, I knew it wouldn't go anywhere.